For this problem, we will use the fact that the induced EMF is minus the change in magnetic flux with respect to time, and we know that the magnetic flux phi b is given by the magnetic field dotted within area element. Since the area element A is perpendicular to the plane loop, then we can say that B and A are going to be in the same direction, and so we can get that this is BA cosine of 0 degrees, or just BA, and we know that the area is constant, so we can say that d phi magnetic with respect to time, we're just going to concentrate on the magnitude, we'll talk about the sign a little bit later, is going to be the derivative of BA with respect to time, and as we said, A is constant, so this is d A times the rate of change of the magnetic field with respect to time. These are given values, so we can say that A, which is 0.012 meters squared, times the change in magnetic field, which is 0.02 Tesla per second, will give us 2.4 times 10 to the minus third volt, or 2.4 millivolts. And now we can use Ohm's law that says that the current is the voltage over the resistance, and we get 2.4 times 10 to the negative 3 volts divided by the resistance, which is 5 ohms, and that gives us a current of 4.8 times 10 to the minus 5th amps. And then if we look at part B, we see that by the resistant becoming high, the resistance will become higher if we change the loop to a insulated loop. And the Ampere's law, as we did above, does not depend on the resistance. So the resistance, the induced EMF, won't change. So loop, let's write this down, loop is insulated, implies that resistance will increase. The fact that the EMF is the rate of change of the magnetic flux with respect to time, this will remain constant. That means that the current, which is the EMF over R, now will decrease because the voltage stays the same and R increases.